Let's look at this problem. We have this shaded area, which is defined by this equation, and we need to determine the moment of inertia, which is the area moment of inertia, about the x and y axis respectively. So let's first try to determine the area moment of inertia of this area with respect to the x-axis. So we know the formula Ix equals to the integration throughout the area of y squared dA. So this dA right here represents the area of the differential element that we choose, and this y right here is the distance, perpendicular distance from this differential element to the x-axis. So how do we choose this differential element? So in this case, we are going to choose our differential element to be a horizontal strip at an arbitrary location y. So this location right here is y. Therefore, this differential element has the width of x and height of dy. So the reason why we choose this differential element is because even though it is made up by numerous particles or numerous little pixel, I guess, but for every particle, the perpendicular distance to the x-axis is the same. Therefore, you can choose a differential element that is, for example, an arbitrary little square at a location x and y. But if you do that, then you will have to integrate with respect to two variables. So in this case, when we choose this horizontal strip, we do not need to integrate with respect to two variables, but only with respect to y. In this case, we should not choose the differential element to be a vertical strip, because this vertical strip, again, is made up by numerous infinite number of particles, but for these particles, the perpendicular distance to the x-axis are not the same. So we should not use a vertical strip as our differential element. So with that said, this is our differential element. So we will have dA equals to the area of this rectangle. The length is x, the height is dy, and because we're going to integrate with respect to y, we need to rewrite x in terms of y. So we have this formula right here, x squared equals to 1 minus x over 4, therefore 1 minus x equals to 4y squared, therefore x equals to 1 minus 4y squared. Therefore, our dA equals to x dy, which is 1 minus 4y squared dy. So now our Ix equals to the integration of y squared multiplied by dA, which is 1 minus 4y squared dy. Now we are integrating with respect to y, and it changes from negative 0.5 meter to positive 0.5 meter. Those are the lower and upper limits for the integration. And this is a polynomial of y squared minus 4y to the fourth power dy. So we integrate that. That equals to 1/3 y to the third power minus 4 over 5 y to the fifth power, evaluated from negative 0.5 to positive 0.5. And after the evaluation, that equals to 1 over 30, or 0.0333 in the unit of meter to the fourth power. That is the unit for area moment of inertia, which is length raised to the fourth power. So that's the first thing done. Now let's move on to find Iy, which is the area moment of inertia about the y-axis. The equation is the same. We integrate throughout the area x squared dA, which is the again, area of the differential element, and x is the perpendicular distance to the y-axis. So obviously we cannot use the same differential element anymore, because this horizontal strip contains points that don't have the same distance to the y-axis. So for that reason, we're going to switch to a vertical strip. So this is our differential element for this part now. Now for this vertical strip, it is at an arbitrary location x, its total height right here is actually 2 times y. So from here to here, that's y. So the total height right here is 2y. And the width here is dx. So with that, dA equals to 2y times dx, and y equals to square root of 1 minus x over 2. If we're only considering this part right here, that is a positive 1 over x square root over 2 multiplied by another 2 dx. So this equals to square root of 1 minus x dx. So that's dA. So now Iy equals to the integration of x squared times square root of 1 minus x dx, integrated from 0 to 1 because x varies from 0 to 1 meter. So I actually use the MATLAB for this part right here. So this is evaluated to be 16 over 105, and that's approximately 0.152 meter to the fourth power. So now we have determined the area moment of inertia of this area with respect to the x-axis, which is also its centroidal axis, because x-axis is the axis of symmetry for this area, therefore it also is the centroidal axis. We also determined the moments of inertia about the y-axis, but notice that the y-axis is not a centroidal axis.